everyone, and welcome to discussion 8. So to start off, some announcements. Written homework 3 is due this Friday, and remember, for homeworks the deadline is at 10:59 p.m. instead of 11:59, so make sure to keep that in mind. And then the project 4, which is on tracking, is due next Friday, so 1 week after the homework. And I'm sure everyone knows this already, but this week there are the elections, so if you haven't voted yet and you're watching this video Tuesday or before, make sure you go vote, and yeah, hopefully the results are favorable. Cool. And then for this worksheet, our focuses are on sampling and then on decision networks. So we're just going to dive right into sampling with a mini lecture. So with sampling, you're essentially trying to determine a probability, and usually it's like your probability of Q, which we call our query variable, given our variable E, and E is representing the evidence that we observed. So we're usually trying to just model all the probabilities in this way. And for sampling, there are 4 main types of sampling that we use. So one of them is what we call prior sampling. And prior sampling is when you sample the parents and then you sample the children given the parents and what happens from these 2 samplings is that you get different counts of the variety of things, and then based on that you can write this probability of Q given E, and that will end up being equal to, or not exactly equal, but about, because remember we are just estimating with our sampling, it will be an estimate of count of Q and E, so both the observed and the given variable over the count of just E. Cool. And this should broadly mirror like when you are thinking in terms of probability, you would want the joint probability divided by the total probability of just the evidence variable, but it's just that since we are sampling, we are using the count instead of like the actual probabilities. So this is the main kind of fraction or formula you're using for prior sampling. And then the second type of sampling is called rejection sampling. And rejection sampling is pretty much the same as prior sampling, so similar to prior sampling, but you ignore inconsistent samples. So inconsistent samples. And inconsistent samples is when the evidence doesn't match. So say you want when like the probability of A given like positive B, but you know that in your sample some of them you got negative B instead of positive, you would just not include those samples when you are forming this fraction because they don't fit what you are looking for. So it basically narrows like the scope of samples we are looking at. Oh. And then the third type is what we call likelihood weighting. So the previous 2 types, prior and rejection sampling, all rate each sample with 1, like they all have the exact same weight. But with likelihood weighting, we are having the weight be equal to the probability of E given E's parents, so given its parents for each sample. So essentially samples that are more likely will be weighted more instead of them all being weighted equally. And then as a part of this, we end up fixing the evidence variables. And something else that is key to likelihood sampling is that notice how for the weight, we are always conditioning on the parents. So that means that we are only conditioning on upstream evidence. So it's only when the evidence is considered a part of the parent, then it is conditioned upon. So that's a key trait to keep in mind for likelihood weighting. And then the last type is what we call Gibbs sampling. Gibbs sampling. And Gibbs sampling is more multi-step, so specifically we have the first step where we fix the evidence, and that just means like setting it to a constant or like to the constant value that we want, and then we initialize other variables randomly. So variables randomly. And then the last step is when we actually repeat. So in this step, we will repeat both choosing or choose a non-evidence variable, let's just call it X, and then we are going to resample X from the probability of X given the Markov blanket of X. And then remember the Markov blanket are the parents, children, and then the parents of their children are all included. And if you need a visualization, the graphical picture of Markov blanket was on both of the past two worksheets. Cool. So then that is the part that is actually repeated. So because of the setup, Gibbs sampling has some traits, and the main ones are that we only update at most one variable per iteration. And that's because in each iteration, so in step 3, we are only choosing one non-evidence variable and then resampling it. And instead of it being distinctly one, it is at most, because it is possible that you resample this variable and you just so happen to get the exact same value. So that's why it is at most. Cool. And then something else I just want to point out is that we never change the evidence variable, because starting in step 1, we are fixing the evidence to be a certain value, and then we go through all these steps and we're only resampling the non-evidence variables. So the actual evidence variable, or like the E, will never get changed. Cool. So yes, that is our general run through on sampling. So now let's actually go through and try a problem. So here we have problem 1, which is Bayes net sampling, and then we have this Bayes net, and then here are all of our distributions. So just starting at part A, we want to use prior sampling, or we used prior sampling and got these results, and now we want to use like the main formula of probability of Q given E is equal to the count of both of them divided by the count of just the evidence variable in order to get a value for it. Cool. So for the first one, we just have probability of positive C. So since there's no given, we can just literally go through and consider all the different samples and then just look for when they are positive C. So if I just go through, we see that positive C, positive C, positive C, positive C, and positive C. So 5 out of the 8 samples have a positive C value, so that would be representative of the numerator, so the 5 samples, and since there are 8 samples total, the denominator would be 8. So that means overall your solution for part A1 is going to be 5, 8. Cool. And then now let's look at part 2. So let me erase the highlights. Cool. So now we want the probability of C, but given that we have positive A and negative D. So a good way to look at this is that you know that it has to be true that we have positive A and negative D. So I'm going to first go through and just highlight the samples that have those two given variables, because if they don't, then we shouldn't include them in this probability because it has this extra given factor. So essentially I will see, let's see, this one has positive A and negative D, this one too, and then this one is the last one. Cool. So in general, we only have 3 main samples to pick from that satisfy this given, but we want to see how many out of these 3 actually has the positive C. So we can see that's 2 because it's here and here. So that means our resulting answer will be 2 in the numerator because there's only 2 samples that have all positive C, positive A, and negative D. And then for the ones that satisfy the given variables, we have 3. So that's why the solution to this part is 2/3. And then now let's move on to part B. So using likelihood rating now. Oh, and something that I did not probably make clear is that in part 2, sorry, I'm looking at the worksheet now and realizing this, is that we are specifically using rejection sampling in part 2. Instead of prior sampling, which is why we first identified these 3 pink highlighted ones as the ones we are actually looking at, because none of the other 5 samples fit our given one, so fit our evidence variable. So that's why, since we are looking at it from a rejection sampling point of view, we automatically did not include them so that it would make our sample, the number of samples we are looking at, smaller. So yes, sorry that wasn't clear, but part A1 is an example of prior sampling, while part A2 is an example of rejection sampling, because we are first excluding the samples that don't fit our evidence variable value, so the positive A and the negative D. Cool. So now let's move on to part B, which is likelihood weighting. And then, yeah, so we want to estimate probability of negative A given positive B and negative D. And right now we have these samples and they want us to write in the weight for each of the samples. So if we look back up on the mini lecture, our weights will be each of the variables that are the evidence and then given its parents. So here we see that B and D are evidence variables, so we want those values given their parents. So specifically, for example, the first one will be the probability of positive B given B's parents, which was A, if we look back here. And it would be specifically given negative A, and that's because in the sample, we drew negative for A already. And this would get multiplied to the probability of the other evidence variable, which is negative D, and its parents was C, and here we got positive C. Cool. And then for the exact values, you can look back up on this picture and get the values just from the table for each one. So that means that here we would have 1/3 times 5/6, and this will end up giving us 5/18. Cool. And then we can do the same thing for the other three. So here we have probability of positive B, but we got a positive A in this case instead. And then we have the probability of negative D, still given positive C. So this, if we look back up on the table, will give us 1/5 times 5/6. So it will end up being 1/6. And then continuing on, probability of positive B and positive A times probability of negative D given negative C. So this will end up giving 1/5 times 1/8, so equal being 140. And then last one times probability of negative D negative C, and this will end up giving 1/3 times 1/8, so it would end up being 124. So our resulting values will be each of these. So the 5/18, 1/6, 140, and 124. Well, and then now we have our weights for each of our sample with likelihood weighting, but we still haven't found the exact estimation we're looking for. Like, we still don't know what this probability is equal to. So now what we're going to do is just consider all the different samples and then add their weights together. So specifically, this will be equal to, kind of similar to prior sampling, where everything is satisfied on the top. So we want to include the weights that have negative A, positive B, and negative D. So that will be, let's see, negative A, so this one, and then also this one. So if we include those two weights, it will be 5/18 plus 124, 1/24, and then over the summation of all of them. So 5/18 plus 1/6 plus 1/40, and then plus 1/24. And if you simplify this, you will get that it's equal to 0.625. So that will be your resulting answer for part C. Cool. So then that means likelihood weighting kind of now has two steps. First, you need to find all the weights and then use those weight values in order to estimate the actual probability. And then looking at part D, the question is whether probability of D given A or probability of A given D is better suited for likelihood weighting, and the solution is going to be that probability of D given A is better. And that's because when you are solving for weights, you are taking each of the evidence variables, so each of the variables after the given, and then conditioning it on its parents. But if we look back up here, D has a parent that is C, but A does not have any parents. So that means when we are looking for the weight of the sample, it will just be the probability of A alone, which is much easier to handle because then it is not conditioning on any other variables. So this also all fits in with how we noted in the mini lecture that likelihood rating is only conditionally on the upstream evidence. So if there's no parents, then there are no conditioning. And that is exactly what is happening for A, which is why overall it is easier to use to calculate probability of D given A with likelihood weighting instead of probability of A given D. So yes, this is our solution. Cool. And then now let's look at part E, which is where we are doing Gibbs sampling. And these are the samples we have gotten. And our evidence is A is equal to positive A. So that means in the first step, when we set the evidence, what we did was set A to be positive A. And here we want to look at these samples and circle the ones that could be generated from Gibbs sampling. So from the mini lecture, we know that Gibbs sampling has two main traits, which is that the evidence never changes and that we only change one variable at most per iteration. So let's just check evidence first. So we know evidence is positive A, and we can see that sequence 1, 3, and 4 are all fine because the A's stay positive throughout. But the issue is sequence 2 because this last one is negative. So sequence 2 cannot be true. And then now let's look at how many variables are changing within each iteration. So I'm just going to circle the variables that or highlight the variables that change. So for sequence 1, iteration 1, and iteration 2, everything stayed the same. And in iteration 3, C became positive. So that is fine. So that means that sequence 1 is a valid Gibbs sampling result. Now let's look at sequence 3. So in the second iteration, D became negative, and then the third one, B became positive. So that's still only at most one per iteration, so it is also fine. So sequence 3 also works. And then now sequence 4. So first one, D became negative, but then both B and D became positive. So that cannot happen because it's two variables changing, so sequence 4 is a no-go. So that means the results that we have are sequence 1 and 3. So sequences are the ones that are valid Gibbs sampling results. Cool. So that's it for problem 1. Now we are going to talk more about decision networks, and we are going to start with a quick mini lecture before diving into the actual problem. So yeah, so with decision networks, we kind of have a different graphical representation, and specifically we have a mixture of chance nodes, which will be denoted with an oval, and then we also have action nodes, which will be denoted with a square or a rectangle. And action nodes are nodes that we are in complete control over because we can distinctly take them, unlike chance nodes. And then the last kind is utility nodes. And utility nodes are usually represented as a diamond. Cool. And then within decision networks, we kind of talk about expected utility a lot, which is why we've defined a value called expected utility. And this happens with the chance node, because if it was just action nodes, you would know your exact utility. So we usually use this in the case of when there's a chance node to consider what we can expect to get on average. And this formula is specifically going to be EU, so expected utility. If we have action A, given that we have evidence lowercase e, this will be equal to the summation of x1 all the way to xn. And that's why specifically we are going with n chance nodes. So all the x are the different chance nodes. And then we would be multiplying the probability of x1 equals x1 all the way to xn equals xn. Sorry, that was a mistake. Given the evidence variable. And then times the utility. So capital U is utility in this case of when you take action A, and then those chance nodes are true. So this formula will give you the expected utility. But usually we don't just want to look at expected utility. You want to consider the different maximums based on your action. Because if you look at expected utility here, we are specifying an exact action. But most of the time, it's more like we don't know which action we should take. And we want to take the one that maximizes our potential result more. So that's why there is this notion of what we call maximum expected utility, and we abbreviate that as MEU, and that is, now you only have the evidence variable, and then it will be equal to the max action of the expected utilities for each action. So essentially the maximum expected utility will let you know what the best action to take is in order to maximize your utility. Cool. And then the other kind of concept in decision networks is this idea of what we call the value of perfect information. So in each of these cases, we have some type of evidence that is result, and it's given by E is equal to lowercase e. And there is kind of just this idea that if you observe more information, how much more should you know? So that's why the formal definition of the value of perfect information is the amount the agent's maximal expected utility is expected to increase if we observe some new evidence. So it's specifically indicating the difference that it will be increased. And we can think of this as, if you look at it formula wise, we have what we call VPI, which just stands for value of perfect information, and it will be E prime, which will be the new evidence you're observing, given that your current evidence is equal to lowercase e, and it will be the difference of the maximum expected utility of if you have this new evidence plus the old evidence, so the joint result, minus the maximum expected utility of if you only just know the original evidence you had. And something to specify is that notice that the new evidence we are observing is represented with a capital letter, so that means that it is a random variable. And we need to represent it as a random variable because when we say new evidence, it can be any evidence. So it's not like we are specifying like, oh, if we observe this extra like velocity about the car, but it's just adding any evidence overall, so you don't know what exact type of evidence you will get. So yes, that is why it's represented as a capital letter or a random variable instead. And then we already defined the MEU of evidence E right here, but just to be clear, like if we were to solve this MEU and write it out when we have both the old and the new evidence, then that would just be equal to the MEU of having both, and that would be the summation of E of probability of E prime is equal to that. Same thing, and then MEU of the two. So essentially it's like calculating an expectation where you are going through and summing together each like possibility and then the probability of that possibility. Cool. And then in terms of VPI traits, the ones to note are that the VPI of E prime given E, so what we saw for above when we observe new evidence, is always going to be greater than or equal to 0. Because if you observe new evidence, you are always going to have more information about the probabilities. So in general, you can just gain more information from observing more evidence. And this kind of trait is what we call non-negativity. So the VPI will essentially never be negative. Cool. And some other traits are non-additivity. So you can't just add the VPIs together and have it be the same as the VPI of the sum of the variables. And then the other one is that the order of observation doesn't matter. So you can observe like evidence B first and then evidence A, and that will be the same as observing evidence A and then evidence B. Cool. So now that we are done with the mini lecture, we're going to go through solving the problem. So here we have the problem. So decision networks, and yeah, let's just go through it. So we're at a car shop, and there's different tests at different costs, and you want to see if you want to buy the car based on the outcome of the test. So we're trying to see whether we should buy car C, and if there is time to carry out at most one test. And that test costs $50 to help us figure out whether we want the car or not. And a car can be in good shape, which is represented by positive Q, or bad shape, which is represented by negative Q. And then the test will maybe help us, and the test can either be a pass or a fail. And car C costs $1,500, but its market value is $200 if it's in good shape, and $700 in repairs if needed. And then C is 70% of being in good shape. And here specifically like decision network that we are using. Cool. So let's just look at part A directly. So it says we want the expected net gain from buying car C, given that we don't do any tests. We just are directly going there and buying the car. So that means we essentially want the expected utility of, I'm just going to call it buy. And this will essentially be how much you're expected times each probability. So let's just consider when the car is in good shape. So we want the probability that the car, or I think it's denoted specifically with Q, is equal to positive Q for good shape, and then times the utility, positive Q and buy, plus the probability when it's in bad shape, times the associated utility. And you're still buying. Cool. Sorry, this got very messy. Yeah, that's better. Cool, so that would be equal to, it says here that we have 70% of it being in good shape, so 0.7. And then if we end up buying it, we will end up getting $500 because we will buy it for $1,500, but it's actually worth $2,000. But if it's actually in bad space, which has a 0.3 chance, then we will end up losing $200, so negative 200, because we buy for $1,500, but then we spend $700 on repairs, totaling to $2,200, but its cost is only supposed to be $2,000 at market value. So if we saw this, we will get that it is equal to $290. So the expected utility from buying is $290. So overall, pretty good. And I just want to point out that when calculating expected utility, it's kind of like using just the total probability rule. We are just kind of considering each case and then multiplying by its appropriate probability. And yeah, or it's also like calculating the expectations. So just wanted to point that out because you kind of see how all of these like common probability formulas and ways of solving come into play with all of these like new terms. Cool. And now let's go to part B. So part B has given us the new information that the probability of a test passing if the car is actually good is 0.9, and then of a test passing while the car is bad is 0.2. And we want to be able to calculate the probability of the test passing, failing, and then the probability of the car being good or bad given whether it passes or fails. Cool. So let's just start with the probability that the test is equal to pass. So here we can just directly use total probability and solve. So that would be equal to probability of the test passing given that Q is positive times the probability that Q is positive, and then plus the probability of the test passing still, but given that the Q is negative, and then the probability that Q is negative. Cool. So from above, we know that this first value is 0.9, and then the probability that Q is good from the previous part we know is 0.7, and then here we know that that term is 0.2, and then the opposite value is going to be 0.3 because it's 1 minus 0.7, and then this will end up giving us 0.69 as a result. So for a probability of passing, the result is going to be 0.69. Cool. And then now we want the probability of the test failing. Test equals fail. And for the test, there's only two choices. You can only either pass or fail it. So here we can directly solve it just by doing 1 minus the probability of t equals pass, because we know that the resulting sum of the probability has to be equal to 1. So then this will just be equal to 0.31. Cool. So this is the second answer. And then now we want to find the probability of Q is equal to positive Q and T is equal to pass. So usually when I see something that asks me to solve for the probability of something given something, I automatically think Bayes' rule. And then in order to confirm whether I should go with Bayes' rule, I kind of look at the existing probabilities I already have. So if we see here, the problem gave us this probability of pass given positive Q. So kind of the opposite, so the flip. So like if you take the bar and you like reverse it, for example, and usually when you see something like that, it's a good indication that you should use Bayes' rule, because Bayes' rule essentially relies on the opposite given probability. So yes, that would be my hint to you. If you see like a given probability and you see the flip of it as a value you already have, then Bayes' rule is definitely like the rule to use in order to solve this probability. So yeah, so let's use that. So on top we would have the probability of t equals pass given positive Q, and we would want to multiply it by the positive Q. And then the bottom will just be the probability of t equals to pass, which we already have from the previous thing we just solved, so we don't need to write that out in more detail. So yeah, so we plug this in, we will end up getting 0.9 and then times 0.7 over the 0.69 we got. So then this will then be equal to approximately 0.91. And then now let's do the opposite case, where it's the probability of Q being negative Q. Sorry, positive Q still. Did I write that down wrong earlier? Oh, yes. This is supposed to be... Wait, let me calculate the probability a car will pass or fail, and then the probability that is in good or bad shape given each test outcome. Okay, cool. So yes, I'm going to calculate whether it's positive Q. So this was supposed to be positive Q. Sorry about that. So now we are going to calculate the opposite. So whether it is positive Q given T is equal to fail. And then same thing as before. This is a good chance to use Bayes' rule because we have the different values for each case because we have given and then we can subtract. So this would just be equal to the probability. T is equal to fail given that Q is equal to positive Q, and then times the same thing as above over the total probability that T is going to be a fail. So if we look here, we know that the probability of T passing given positive Q was 0.9. So that means the probability of T failing given positive Q must be 0.1 in order for the sum to still be equal to 1. So that means this has to be equal to 0.1 times 0.7 over the 0.31 we found before. And that will be about 0.22. And then looking on the specifics of the problem, we also want the case when the car is bad and then with each test. But now that we have these two, it's very easy to solve. So specifically, probability of Q is equal to negative Q, so in bad shape, given that T is equal to pass, will just be equal to 1 minus the situation of when the car is in good shape. Because if you pass the test, there's only two results. Your car is either actually in good shape or in bad shape. So the two have to sum to 1. So this will be about equal to 0.09. And then we can do the same thing for the other case. So probability of Q is equal in bad shape, given that the tests fail. And that will be equal to 1 minus the situation when the car is in the good shape, given that tests fail. So then that will be about 0.78, so just 1 minus 0.22. So that was a lot of probabilities to solve, but we have finished up part B. So now let's go on to part C. Cool. So now we want to calculate the optimal decisions given whether the test passed or failed, and then their expected utility. So whenever we are looking at the optimal decision, we need to take maximum expected utility into account because that's when you actually consider different ones. But before doing that, let's first calculate all the different utilities so we can just look and easily pick from it. So there's 4 different combos. One of them is you buy it, given that the test is actually a pass. And this will just be equal to the probability that the car is good, given that it was passed, and then times the utility of positive Q and buy plus the probability that the car is not good, given t is equal to pass. Oh, that did not show up. Cool. Given that the utility is not good, but you still end up buying it. Cool. And we can use the previous values we got, so 0.91 times, if you end up buying it, you will gain 500, like what we talked about in part A. That is a 5. Cool. And then if it is not good, but it still passed, then 0.09, and you will lose 200. So that will end up being about 437. Cool. And then the next case we can look at is whether you buy, but the test was a fail. So then in this case, you would look at basically all the same things, but each of the passes will become a fail instead. So I'm not going to write it all out again, but essentially the passes will be replaced by the fail. Cool. And then this will then be equal to the 0.22 from the previous part times 500, and then 0.78 times negative 200, and that will be equal to negative 46. And then the other two are easier to solve because we just have EU of if you don't buy, whether it's pass is going to be equal to the expected utility of whether you don't buy, and then T is fail because you aren't buying, so you aren't spending any money, so this will just be equal to 0. So then based on this, your maximum expected utility of buying, your maximum expected utility if T pass, but you don't know what action to get yet, is going to be 437 with buy, because 437 is greater than 0, and then your maximum expected utility when the test fails is going to be equal to 0 with not buying, because 0 is greater than negative 46. So that is how you consider maximum expected utility into account, and it was helping you choose the action of what you should do depending on the result of the test. Cool. So now we are going to calculate the value of perfect information of tests and then use that value to determine whether the buyer should pay for the test or not. Cool. So if we look at the VPI of tests and just writing out the formula, you want to consider the situations of maximum expected utility of the added information given the result, but remember we don't have all the different types of information. We don't know what evidence we are getting. So the evidence we are adding is the result of the test, and the test can either pass or fail. So we want to consider the probability when the test is equal to pass, and then multiply that by the maximum expected utility of pass. But we also need to consider the probability of when test is equal to failing times the maximum expected utility of the test failing. Cool. And then there's only 2 results we can get from the test, so having just these 2 terms is enough. And then that is the maximum expected utility given that we observed this new information. And we need to subtract it by the original maximum expected utility of what you originally have, and that's usually sometimes just denoted with this. Cool. So if we take all the values we originally had, then we have that there was a possibility of 0.69 of the test passing, and that will be multiplied by 437 with the buy, and then for failing is 0.31. It was just 0, and then we will be subtracting 290, because if we scroll back up to part A, the maximum expected utility of just buying without knowing anything but the test was 290. So that is where we're getting this value from. Oh. And then here, and then if we simplify this out, we can get that the VPI of the test is equal to about 11.53. So essentially, getting this new information help us for like $11.53 worth, that type of idea. So that means that we should not buy the test, because the test is $50, but getting this new information from the test only helped us for $11.53, so it is not worth spending this extra $50. So it's only because 50 is like greater than 11.53. And yeah, so that's our solution. This is the VPI of test, and then we should not buy the test. And then yeah, that wraps up this worksheet.